What's up, class? Hope everyone's doing okay at home. So this is the beginning of our next module, which is kind of using Fusion 360 as a modeling tool, a simulation tool, and then an analysis tool. So kind of another way to look at the engineering design process that I personally really enjoy, which is why I wanted to do this. I studied structural engineering at Virginia Tech and went to grad school for it, and have always been kind of obsessed with skyscrapers and architecture in general. Which kind of builds the theme of this module. So quickly, let's go over kind of the history of the tallest buildings in the world from like 1908 to present time. Okay, and most of these actually were in New York City up until the end of the 20th century. So I don't know as much about these early buildings, but kind of just want to show you the progression of the height and over the time it did. So as you can see, the tallest one in the world kept changing a bunch in the early 20th century, and then around 1930s when it really got exciting, with the Chrysler Building being over 1,000 feet in New York City, which is one of my all-time favorite buildings. And then the Empire State Building was built 1 year later. It was the tallest building in the world for 40 years at a height of 1,250 feet. It took until 1971 when the World Trade Center was built for it to be surpassed as the tallest building in the world. And then if you fast forward to present time, the tallest building in the world right now is the Burj Khalifa in Dubai, completed in 2010 and standing at about half a mile tall, which is definitely insane. So this is just another graphic to look at the progression of the buildings and to give you just a better idea of really how much they've grown. But what I want us to focus on is why did it take the world 40 years to build a building taller than Empire State Building? There was a big surge of skyscrapers in the early 20th century, but it took till 1971 to kind of see that moving forward again. So let's start with this question. What is the controlling load for any tall building? You might think weight, you might think the people in it, you might think the actual weight of the materials, but what it actually, but I want you to think about what force gets larger as you get higher above the ground. And you feel this like if you're on an observation deck at any tall structure, or even if you're on a mountain or at the top of a roller coaster, and that's there's a hint, but it's wind. Okay, so the taller you get, the higher or the stronger the wind is. Okay, so engineers need to laterally brace buildings against the wind, because once again, as height increases, so does the pressure from the wind, which is seen in this graphic here. Okay, and that's kind of just how it's represented and used in calculations. Small buildings, it's simple, like the school, like even your house, but I'm thinking more industrial buildings like schools. This is an example of shear walls. So in small concrete buildings, shear walls take the loads from the wind to kind of brace it laterally. So as the wind pushes this way, this wall resists the wind. And if the wind's pushing this way, these walls resist the wind. Steel buildings, you might have actual lateral bracing. Okay, so as it pushes this way, these diagonals are in tension, these are in compression. If the wind pushes this way, these are actually now in tension, these are in compression. Okay, so the lateral load is taken through these lateral bracings, or you have thicker walls and thicker columns and thicker beams. Okay, and this is creates moment connections, which kind of resist the lateral bracing through the actual connections here. Okay, but for small buildings, it's pretty straightforward. But as height increases, the stiffness of a building decreases exponentially. So I think a way to think about that is like if you're in the middle of the mesa room and you find one of those long PVC pipes, and as a lot of you love to do, you start like shaking it around and it's easy to flex, right? But if you cut that 6-foot PVC pipe, or however long it is, down to like a 6-inch one, it's much harder to bend. Okay, so once again, buildings work the same way. So as they get taller, they're much more flexible and lose a lot of their stiffness. So not only does the wind load increase, but we lose stiffness. So the cost need to keep a building safe increase dramatically with height. So after the Empire State Building, the companies that were building these kind of realizing that the cost benefit of going higher than that wasn't really worth it. And that race of tall buildings kind of stopped until this dude came along, Fazlur Khan. So Khan was an engineer He went to University of Illinois and worked for Skiddings Owen Millmore, I think. That's off the top of my head, but it was based in Chicago. It was an engineer architecture firm. So he focused on the wind being the controlling load, and then that the lateral stiffness of the building was the controlling factor of the design. So like we just talked about. So how could he overcome this? So he realized that buildings would be most effective if they acted as a single cantilever coming out of the ground. So cantilever, think of a diving board, an awning, but it's something that's just supported at one end, okay, and loaded from above. So there's a simple cantilever, but kind of he viewed it as like a cantilever like this coming out of the ground with the wind going against it. So what he had to do is have these buildings act as single cantilevers, obviously very, very large cantilevers instead of individual members like it was designed for us before. Okay, the next video is going to be looking at understanding the design of a cantilever, so we can kind of understand how that deals with skyscrapers. But I want to stop there so we keep the video short. Okay, thank you.